All right, this is FRQ from 2001, question number 3. Let's get busy with it. Okay, our first, let's just read it first. Let's try to see if we can understand what's going on. The car is traveling on a straight road with a velocity of 55 feet per second at time t equals 0. Velocity of 55 feet per second. If you're working on decoding or making sure that you understand what you're reading, underline words that are key to what you're trying to do, like key calculus words that pop out at you. All right, that's feet per second at time t equals 0. For 0 to 15 seconds, that's 18. Where t is. That's 18, thank you. The car's acceleration, acceleration a of t in feet per second squared is a piecewise linear function defined by the graph above. Actually, it's to the right. Okay, so this is a. It's acceleration, which also equals v prime. Okay, this goes back to a common concept in calculus. We have f prime, f double prime. Normally, this is velocity or speed. Okay, and then when we take the derivative of velocity, we get acceleration. If we do the antiderivative of velocity, then we're going to get amount. It looks like this problem isn't even considering this, and we're starting with this. And so, if acceleration, that's normally represented by a, is given to us, then this is actually the derivative graph for velocity. So we have a derivative graph right here of velocity. Okay, making sure we see that and understand that. Now let's read this. Is the velocity of the car increasing at t equals 0 seconds, or equals 2 seconds? Why or why not? Okay, so what's our current velocity? Doesn't it tell us? Tell us it's 55 seconds, or feet per second. That's our current velocity. It's a positive velocity. So we're starting at 55 feet. I'm just going to write this down because it's pretty important to my answer. Feet per second. We are currently going that fast at 0. Is the velocity of the car increasing at t equals 2? So I go over to 2. And I go up and look at my graph. Now something that points out, or like kind of strikes me really fast, is that this is a point right here on my acceleration graph. I don't know if that tells me anything to my answer, but that's a point. Functions are not differentiable at points, and so that popped out to me. But how do we answer this question? It says, is the velocity of the car increasing at that? Okay, so how do we know if a velocity is increasing? If a velocity is increasing, what would be true? Like if your speed is increasing, what would be true about your acceleration? Would your acceleration be 0, for instance? No, you would have a positive acceleration, right? Right? Okay, so at t equals 2, do we have a positive acceleration? Yeah, acceleration is 15. So I'm going to say, let's see, how do we say that? Because it says why or why not. Let's see, is it increasing? Yes. Velocity is increasing. How do we know this? Well, a of t equals the derivative of velocity. A is the derivative of velocity. And if a is the derivative of velocity, that means if v prime is positive, we know that the velocity v is increasing. So I can just say, I guess I could just say because, man, is that and v prime is greater than 0 at t equals 2. Oh, you know what I could have written? I could have just put a t right there. I could have said v prime of t is greater than 0. So, because we're greater than 0, because we have a positive acceleration, we know that we are increasing. Okay, at what time, the next question, at what time in the interval, other than t equals 0, is the velocity of the car 55 feet per second? Now, that's kind of a weird question. How fast are we going at t equals 0?
55.
We're at 55 feet per second. Okay. Here's a crazy question. How fast are we going at 2? At 2. T equals 2. How fast are we going? No, not 55. Now, if I wanted to find the velocity, and I'm given A, I'm given the acceleration. If I want to find velocity, wouldn't that velocity value be the area underneath my acceleration curve? Now it's a mouthful. That is such a calculus-like sentence I just gave you guys. Because before, like, there's other problems that you guys have gotten f prime, and you're trying to find the amount. And when you're given f prime and you want to find the amount, don't you just find that area underneath the curve? Mm-hmm. That's exactly what we're doing here. So if we've been accelerating for 15 for 2, or was that 2 seconds? For 2 seconds, wouldn't we have a greater speed now?
Yeah.
We should have a greater speed than 55. So what is the area underneath this curve? What is the area of that?
30.
Yeah, it's just 2 times 15, 30. So we are actually going at t equals 0. So v of t, or 2, which is not this function, it's not this graph. V of 2 should be 55 plus 30. 30 is the area of this. So how fast are we going at t equals 2?
85.
We're going 85 miles an hour. So the question is, see how it's like all about understanding this problem? The question is, where else are we going 55 feet per second? So now your whole thinking on this problem is probably, I'm hoping that it's changed, because now you're just thinking, well, if all of this right here is causing me to go faster, because if I find the area of this, I would just add that to 55 to find out my current speed, then I need to take that same area away to find out the t that would give me 55 feet per second again. So these areas are exact opposites of each other. Would you guys agree?
Mm-hmm.
Yeah, they're exact opposites. So at 12, at t equals 12, we are back to 55 miles per hour. Now, when acceleration is going below the x-axis here, does that mean we are going 0 miles per hour, or that we're going a negative speed, a negative velocity? No. All this means is that we're slowing down. We are decelerating. When acceleration is negative, we are decelerating. Okay, I want to pause for a moment to try to help you guys understand the concept that's going on here, because I can very easily lose you on this. All right. Now, if I have acceleration, you guys know, I hope, that if you do the antiderivative of acceleration, you get velocity. If you go this way, you're doing the antiderivative. If you're going this way, you're doing the derivative. Okay, so this doesn't look like an A. Let's change that. So let's draw a graph that's totally unrelated to what we're doing right now. If I have velocity, and velocity looks like this, and it goes like this, it's like this little parabola thing. And right here, we're going to say this is 7, and right here, my maximum point right here was going to be 100. So this is my velocity graph. And then over here, what would my graph look like for acceleration? Well, it looks like the speed is increasing until I get to the 7. And so it looks like acceleration is going to be positive, and then the acceleration goes negative. So here's my acceleration. Here's my velocity. The connection between these two is pretty significant here. It's very important. What do you think the area of this little triangle is that I have is right here? The area of this equals 100. It's the same. The area underneath a derivative curve will give you the y values for the previous graph, for like the antiderivative of that. And so here, let me write this a different way. What's another way to write this function? Instead of writing v of t, I can actually write it as the antiderivative of acceleration. But to make it legit, I'm going to need to have a constant, put an x right here, and say this is v of x. So this velocity function can be written as an integral function. The area underneath a derivative curve will give you the y values for this. So how does this relate to this one right here? Well, this says at what time in the interval other than 0 is the velocity of the car going 55 feet per second. Well, at the very beginning, when there was no acceleration being recorded, at t equals 0, we are going a velocity of 55 miles per hour. And then, as acceleration is happening, our speed is increasing. The area underneath this curve is speed. And so our speed is increasing. So we would have to take away that same speed so we can get back to 55 miles per hour. That's only at 12 our t equals 12, are we going 55 miles per hour? So how would we say that for our answer? So we got at what time, velocity, y. Okay, at t equals 12, we are going, I'm just going to say it like this. V of t equals 55. How do we know that? I'm going to say the area underneath the acceleration curve from 0 to 6 minus the area from 6 to 12 underneath this curve equals 0. So therefore, we're back at 55 miles per hour. Okay, that's sufficient. All right, let's do the next question. All right, this question says, on the time interval from 0 to 18, what is the car's absolute maximum velocity? Now, if you understand that the area underneath this curve equals the velocity, then this actually doesn't seem to be that bad. Now, what time does it occur? Justify your answer. Okay, acceleration is the derivative function of velocity. Correct? Correct? Yes, yes. So that means if we were to do a sine line graph right here, we would have a critical point at 6, and we would have a critical point at 16. If we were looking for an absolute max, that means we would also have to consider 0, and we would also have to consider, 16 is in the way of 18. No, wait, yeah, 16 is right there. Okay, we'll say 18 is right here. We'd have to consider all these x values for an absolute max or absolute min. So let's think about this for a second. Which ones should we consider? Which ones should we not consider? The slope of the velocity function is positive because acceleration is above the x-axis right here. And then the slope goes to negative because acceleration then dips below the x-axis. So right here we have positive and negative, positive and negative. Looks like we have a max possibility at x equals 6 or t equals 6. We do not have one at 16. Why do we not have one at 16? Because we're going from negative to positive slope. Not going to happen. All right, so now we have to try 18, we have to try 6, and we have to try 0. 0 is actually not that bad. When t equals 0, you guys know what the velocity is. When t equals 0, actually let's write it like this. We'll say v of 0 equals 55. Oh, that one was simple. A, B, C. Okay, what about v of 6? What was that one? I think we already figured that one out. No, we didn't. We have to find the area underneath this curve right here and add it to 55. So we're going to say 55 plus the extra speed that we gained from the acceleration. So we're going to find the area underneath this curve. How do we do that? We're going to go, I'll break it up into a triangle and a square or rectangle. You guys can use a trapezoid rule or whatever you want. So this is going to be 2 and 15, or trapezoid. So that's going to be 30. So I'm going to add 30 to it. And let's add the area of this triangle. That's going to be, from 2 to 6 is 4. And the height is 15. So it's 1/2 base times height. What's half of 4? It's 2. 2 times 15 is 30. So we're adding another 30 to it. So this equals 60 plus 55, which is 115. So I have 115 miles per hour. This is 50. No, dang it, it's not miles per hour. What is it? Feet per second. Man, I want to write mph. And I got to try one more. V of, what was it, 18? Okay. All right, so then we already got 115. So we're going to add to that. Actually, wait a second. We know at 12, we're back at 0. Right? No, not 0. We're back at 55. That's what we said at B. So let's not do 115. Let's just say we're at 55. So we need to find the area from 2 to, what number is that? 12 to, this is 16? Yeah, I X'd it out right there. Let's see. Okay, from 12 to 16, I got to find the area of that. So let's find the area of that. That would be, that's 2, and that's negative 15. So that's negative 30. So I add negative 30 to it. And then what's the area of that little triangle right there? That's going to be 2, and then negative 15 again. So, I mean, 1/2 base times height. Let's write it out this time. I won't do it all in my head. 1/2 base times height, which is negative 15. What do I get? That's going to be just negative 15. Yeah. negative 15. And then I have to add that last area right here. Let's do this one in our head. What would that be? 16 to 18 is 2, and this is 15, so it would just be 15. So these cancel out. And negative 30 plus 55, is that going to be greater than 115? No, so this is our max right here. Okay, and then all the work is my justification. I identified that as my max. Okay, so that's our max. Now let's look at the last one. At what times in the interval from 0 to 18, if any, is the car's velocity equal to 0? Justify your answer. At 16, are we at a velocity of 0? That's the only spot that we can be at a velocity of 0, right? Because we have all this negative right here. We know that at 6, our velocity is 115. And we know at 12, our velocity is 55. What was the total area right here of this guy? It was negative 15. No, negative 30 and negative 15? Negative 15 and negative 30. So that's negative 45. So at T, let's see, at V of 12, we know that we're at 55. So V of, what was that, 18? 16. 16, that would be 55 plus negative 45, which equals 15. Nope. This would be the lowest speed. That's our minimum value. And so we never get to 0. So you just have to state that to finish off your problem. All right, not 15. 10 feet per second. So we never get to 0.